Let's imagine that you're a big data company. You have a massive amount of data, more than it can ever be stored on one computer. Hold on, we need to have good branding for our big data company. That is more important than any technical problem. Since we are a big data company, we should name ourselves after a big number. How about Aleph, which is the symbol we use to represent how big infinite sets are? No, that would be too simple for a trademark. Well, there are also the Beth numbers, which are closely related. So our company should be called Aleph Beth. I can see no trademark problems with that name. So Aleph Beth has records about people, a ridiculously large number of user records. Each record has the things you would typically want as a big data company: age, gender, a scarily accurate estimate of income, and all of those persons' interests. We have so much data on so many people, it is impossible to store it all on one machine. So we have to use multiple computers, all storing a part of this list. But having all this information isn't going to make us rich. We need to be able to process it. But if it's spread across all these machines, how can we process all that data and do it in a time-efficient manner? Google solved this problem by using a technique they call MapReduce. In order to explain MapReduce, we're going to have to talk about functions. I did a whole separate video all about functions, which you can find here. But the short version is, functions are a thing that takes an input and returns an output. The unfortunately named map of MapReduce is a higher level function, a function that takes another function as one of its inputs. The first argument to map is a function that takes a single argument and returns a single value. The second argument is a list of values. What map then does is apply the function to every item in the list and create a list of outputs. In a way, map is like an automation feature. It takes a single one-off process and applies it to many things. Because each application of the map function is independent, not affecting any of the other applications, it can be done in parallel, and it can be done across all the machines at the same time. The other half of MapReduce is a higher order function reduce. Reduce takes as its arguments an operation and a list. An operation is a function that takes two arguments of the same type and returns a signal value of that type. Plus, times, minus, these are all operations that you are most likely familiar with. Reduce applies the operator pairwise to every item in the list until there's only one item left. For example, if you have reduce with plus as the operator and a list of numbers, it will return the sum of that list. This doesn't just work for numbers. If the operator is the string concatenator and you have a list of strings, then the reduce function will concatenate them all into a single string. The reduce function also works well in a distributed environment. With a large list, we can assign separate machines to process part of the list and then have the separate parts further reduced by a consolidating machine. Depending on the size of our task, create a hierarchy of machines, all consolidating down to a single result. So, with these two powerful tools, let's start processing our data. Broadly, MapReduce works by passing a list through map and then reducing the items into a single output. An example will make this so much easier. Let's count up how many people are interested in VTubers. The function we will give to map will take our customer record and return 1 if the customer has that interest and 0 if they don't. The operator we will give to reduce will be addition. The list of zeros and ones will get sent to a common server, and then the reduce operator adds them all up. At the end, the result we will get is a count of the number of VTuber fans in our data. However, what if we wish to get more than a simple count? How about calculating the mean average income? We can have our map function return a pair of values. The first value being the income, if they are a VTuber fan, 0 otherwise, and the second value being 1 if they are a VTuber fan, and 0 otherwise. This time our reduce function will return the first values added together and the second values added together. After all the additions, all we have to do is divide out the total income with the total count, and we'll get the mean income. But we could do more than just have a single value in our list. We can create lists of lists. For example, we could produce a list of everybody who is interested in socio-political ramifications. The way we would do this is to use a map function that returns an empty list for a consumer with no interest, and a single member list where there is a link interest. Then we could use the list concatenation operator as our reduce function. This would give us a list of people who are interested in that topic. What if we wanted a sorted list? Well, rather than using list concatenation, we can use list merge. A merge takes two sorted lists and merges the items of those lists into a sorted list. Now, a list with only one item is in the correct order. So, if you keep merging lists of the same size together, you get a sorted list matching our requirements. Clearly, MapReduce is a powerful technique, but what types work well with it? Knowing that would make programming new uses of MapReduce simpler. Well, let's look at the operator. In order to be able to span the reduce step across many machines, we have to be able to nest the operator arbitrarily. In other words, the operator has to be associative. The other thing we require is an identity value. That is, a value where the operator does nothing. This is so that we can have a way of clearly eliminating unused records. So, we need an associative operator with an identity value. That's right, we need a monoid. This is what is awesome about monoids. If you can transform your problem into a monoid, then you can solve that problem using reduction. And since the monoid has such a simple requirement, it can be used for so many things. Monoids are an extremely versatile tool, and that's why I love them so much.